Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to discuss on the different digital communication channels. Communicating data from one location to another requires some form of pathway or medium. These pathways are called communication channels. A channel, in a simple way, provides the electrical connection between the source and the destination. We have a very large number of communication channels available in the current technology, such as pair of wires, coaxial cable, optical fiber, radio channel, satellite channel, or a combination of any of these is also considered. The communication channels have only a finite bandwidth, non-ideal frequency response. The signal often suffers amplitude as well as phase distortion as it travels over the channel. Also, the signal power decreases due to attenuation of the channel. The signal is corrupted by unwanted, unpredictable electrical signals, which are also referred to commonly as noise. Some of the most important parameters of the channel are signal to noise ratio, commonly referred to as SNR, usable bandwidth, amplitude and phase response, and lastly, the statistical properties of the noise. The two channel characteristics, bandwidth and power, constitute the primary communication resources available to any designer. In fact, the details of modulation and coding used in the digital communication systems depend highly on the characteristics of the channel as well as the application of interest. Other channel characteristics of particular concern are the degree to which the amplitude and phase responses of the channel are determined, whether the channel is linear or nonlinear, and how free the channel is from external interference. In this particular session, I will be discussing on these issues in the context of five specific channels, which are telephone channels, coaxial cables, optical fibers, microwave radio, and lastly, satellite channels. I'll be starting with the telephone channel. A telephone channel is designed to provide voice-grade communication. It is built using twisted pairs for signal transmission. A twisted pair consists of two solid copper conductors, each of which is encased in polyvinyl chloride, commonly called as PVC sheet. Twisted pairs are usually made up into cables, with each cable consisting of many pads in close proximity to each other. During the last century, telephone channel has evolved into a worldwide network that encompasses a variety of transmission media such as open wire lines, cables, optical fibers, microwave radio, and satellites, as well as a complex of switching systems. This makes the communication channel an excellent candidate for data communication over long distances. Twisted pairs are naturally susceptible to electromagnetic interference, referred to as EMI, and to reduce this effect, the wires are commonly twisted. The channel has a bandpass characteristic occupying the frequency range from 300 to 3400 Hz, a high signal to noise ratio of about 30 dB, and approximately a linear response. For the transmission of voice signals, the channel provides flat amplitude response. But for the transmission of data and image transmissions, since the phase delay variations are important, an equalizer can be used to maintain the flat amplitude response and a linear phase response over the required frequency band. Transmission rates up to 16.8 kilobits per second have been achieved over telephone lines. Now we move on to the next channel, which is the coaxial cable. A coaxial cable consists of a single wire conductor centered inside an outer conductor, which are insulated from each other by means of a dielectric material. The inner conductor is made up of copper wire encased inside the dielectric material. As for the outer conductor, it is made up of copper or tinned copper or simply copper coated steel. Typically, a coaxial cable has a characteristic impedance of 50 or 75 ohms. Compared to a twisted pair cable, A coaxial cable offers a greater degree of immunity to electromagnetic interference. The two primary advantages of coaxial cables as a transmission medium are a relatively wide bandwidth and freedom from external interference. However, their operational characteristics require use of closely spaced repeaters. Indeed, efficient digital transmission systems using coaxial cables have been built to operate at a data rate of 274 megabits per second with repeaters spaced at 1 kilometer intervals. A common application of the coaxial cable is as the transmission medium for local area networks in an office environment. Another common application of coaxial cables is in cable television systems, also known as community antenna television systems. In this particular application, coaxial cables are used to distribute television, audio, and data signals from the head end to the subscribers. The head end is the central originating unit of the CATV system where all the signals are carried and then processed. Let us now move on to the next channel, which is the optical fiber. An optical fiber is a dielectric waveguide that transports light signals from one place to another. It consists of a central core within which the propagating electromagnetic field is confined and which is surrounded by a cladding layer which is itself surrounded by a thin protective jacket. The core and cladding are both made up of pure silica glass, whereas the jacket is made up of plastic. The basic property of light is that when a ray of light passes from a medium of high refractive index to another medium of low refractive index, the ray is bent back toward the medium with the higher refractive index. Accordingly, if a ray of light is launched into an optical fiber at the right oblique acceptance angle, it is continually refracted into the core by the cladding. That is, the difference between the refractive indices of the core and the cladding helps guide the propagation of the ray of light inside the core of the fiber from one end to the other. Compared to coaxial cables, optical fibers are smaller and they offer high transmission bandwidths and longer repeater separations. Optical fibers have unique characteristics that make them highly attractive as a transmission medium. In particular, they offer the following characteristics that are listed in this slide. They have enormous potential bandwidth resulting from the use of optical carrier frequencies of around 2 into 10 to the power 14 Hz. With such a high carrier frequency and a bandwidth roughly equal to 10% of the carrier frequency, the theoretical bandwidth of the light wave system is around 2 into 10 to the power 13 Hz. Optical fibers have low transmission losses as low as 0.1 dB per kilometer. They have immunity to electromagnetic interference, which is an inherent characteristic of an optical fiber viewed as a dielectric waveguide. They are small in size as well as weight, which is characterized by a diameter no greater than that of a human hair. They also offer ruggedness and flexibility, characterized by very high tensile strengths and the possibility of being bent or twisted without damage. Moving on to the next channel, which is the microwave radio. A microwave radio channel operates on a line of sight link. It consists basically of a transmitter and a receiver that are equipped with antennas of their own. The antennas are placed on towers at sufficient height to have the transmitter and receiver in line of sight of each other. The operating frequencies range from about 1 to 30 gigahertz. For a large fraction of the time, in most locations, the propagation conditions do not vary significantly from a direct line of sight path between the transmitter and receiver. Under such conditions, the radio channel operates as a non-dispersive transmission medium capable of highly reliable, high-speed digital transmission. At other times, however, anomalous propagation conditions develop in the channel due to meteorological variations, causing severe degradation in the radio system's performance. These conditions manifest themselves in a phenomenon known as multipath fading. The term multipath refers to the fact that the propagation between the transmitter and receiver takes place along several paths of different electrical lengths. The receiver thus sees a weighted sum of delayed replicas of the transmitted signal from these multiple paths, interfering with each other constructively or destructively. Consequently, the received signal experiences fading in that its amplitude varies with time. When the replicas arrive at the receiver in phase, they reinforce each other. However, when they arrive in antiphase, they cancel each other. In order to design a digital radio system to work in such an environment, it is therefore necessary that provisions be made to overcome the effects of multipath fading. Moving on to the last channel of the discussion here, the satellite channel. A satellite channel provides broad area coverage in both a continental and an intercontinental sense. In almost all satellite communication systems, the satellites are placed in geostationary orbit. For the orbit to be geostationary, it has to satisfy two requirements. First, the orbit is geosynchronous, which requires a satellite to be at an altitude of 22,300 miles. A geosynchronous satellite orbits the Earth in every 24 hours. Second, the satellite is placed in orbit directly above the equator on an eastward heading, that is, it has zero inclination. A satellite channel consists of a satellite in geostationary orbit, an uplink from the ground station, and a downlink to another ground station. Typically, the uplink and downlink operate at microwave frequencies, with the uplink frequency higher than the downlink frequency. On board the satellite, there is a low power amplifier, which is usually operated in its nonlinear mode for high efficiency. With the satellite positioned in geostationary orbit, it is always visible to all the Earth stations located inside the satellite antenna's coverage zones on the Earth surface. Thus, the satellite channel may be viewed as a repeater in the sky, permitting communication over long distances at high bandwidths and relatively low cost. Communication satellites in geostationary orbit offer some unique system capabilities, such as broad area coverage, reliable transmission links, and wide transmission bandwidths. The most popular frequency band for satellite communication is 6 GHz for the uplink and 4 GHz for the downlink. The use of this frequency band offers few attributes, which are listed here. First, relatively inexpensive microwave equipment. Second, low attenuation due to rainfall. Lastly, insignificant sky background noise. The sky background noise, which is due to the random noise emissions from galactic, solar, and terrestrial sources, reaches its lowest level between 1 to 10 GHz. That is why we use 6 GHz for uplink and 4 GHz for downlink. Right. So that is all about the discussion on digital communication channels. Thank you for watching. Have a good day.